Lesson 2 is about inverses, and this is the first of 2 days that we're going to spend on inverses. So let's kind of go through. First of all, we're going to do this little investigation into inverses. So I'm going to graph some points here. So it gives me, it looks like 5 points. So the point 0, 6 is right up here. And the point -2, 0 is over here. Remember, all I'm doing is I'm moving left and right with the first number, up and down with the second number. The third point, 1, 9, is going to be right 1 and up 9. It's going to be right up there. And -1, 3 is going to be left 1 and up 3. And -3, -3 is going to be left 3, down 3. So I have all of those points, and then it says graph them, turn it into a line. And we're going to call that f of x. Perfect. All right. That takes number 1 and number 2. Part 3 says reverse the order, the x and the y, in each of those ordered pairs. All right, so instead of 0, 6, I'm going to reverse that and call that 6, 0. Instead of -2, 0, I'm going to do 0, -2. Instead of 1, 9, I'm going to do 9, 1. Instead of -1, 3, I'm going to do 3, -1. And reversing -3, -3 keeps that one the same. That one just stays -3, -3, because the reversing is the same. And now I need to graph these points. As number 4 says, graph the new points. So the point 6, 0 is going to be to the right 6. 0, -2 is going to be down 2. Right 9, up 1. It's right there. Right 3, down 1. It's going to be right there. And then that point is also going to be on there. And then I'm going to create another line. There's my line, and they want us to call that F. Just like the blue one was F, this one is also F, but this one has a -1. So that is the inverse of F, is actually how you pronounce that, F to the -1. All right, so it wants to know, what are some similarities that you see? What are some things that are the same? So things that are the same, they both go through the point -3, -3. They're both straight lines. Some differences. They have different y-intercepts. Those are different. They have different slopes. The slopes are different. That blue slope, if you do the rise and the run, it looks like it rises 3 and runs 1. And then the red one looks like it rises 1 and it runs 3. Well, that's something that could be of note, I guess. So I do have some straight lines that looks like they do share one common point. They both have positive slopes, even though one of them is steeper than the other one. Those are some key differences. So now it wants us to write the equations of the line. So the blue equation, and I'm just doing, y equals mx plus b. I'm going to find the slope, and then b is the y-intercept, so where it crosses the y-axis. All right, so the slope of the blue equation, we just said it goes up 3 and right 1. So I can write 3 over 1 or just 3. X. And then it crosses the y-axis up at 6. So that is 3x plus 6. The red equation has a slope. It goes up 1 and over 3. So it's 1/3 x, and its y-intercept is -2. So those two equations, 3x plus 6 and 1/3 x minus 2. Now it wants me to draw a line segment to connect the mirrored points. Okay, so here are my mirrored points, and I'm going to do yellow here. So when I connect these two mirrored points, there, then connect those two mirrored points there, then connect those two mirrored points there, and these two mirrored points there. So I've connected the mirrored points, and then it wants me to find the midpoint of each of these segments. I'm going to zoom in for you so you can see this. So the midpoint of that yellow segment is right here. The next yellow segment, it looks like 1, 2, 3, it goes across 4 squares, so I would do half of the 4 squares. Midpoint is right here. The midpoint of this next one is right there. The midpoint of the last one is right there. So if I think about the coordinates of these points, of these midpoints, the coordinates down here are, this point is at -1, -1. The coordinates of the second one, this one is at 1, 1. The coordinates of this one are at 3, 3. And then 5, 5. Well, if you think about that, if I were to connect all the midpoints, right? This is what it's asking for. If I were to connect all these midpoints, what would happen? If I were to connect those midpoints, it creates that dotted yellow line. This yellow line, just so you know, is the line y equals x. That's the line y equals x. So when this question down here, number 7, says, find the midpoint of each segment, what do you notice? All those midpoints are, the x and the y numbers are exactly the same. It's like having 1, 1 or 2, 2 or 3, 3 or 4, 4 or 5, 5 or 6, 6. And connecting them makes the line y equals x. That is so important to know. That whole y equals x thing. Super, super, super important to know. All right, the last thing that I want to do in part 8 in this investigation is I'm going to go back to number 6 and I'm going to look at this equation, y equals 3x plus 6. Y equals 3x plus 6. And what they want me to do is they want me to take my y and my x, and they want me to switch these two things. So instead of y equals, I'm going to say x equals. Instead of 3x, I'm going to say 3y plus 6. Because I just need to switch those two things. All right, so now what I want to do is I want to solve this thing for y. I want to solve this. So the first thing that I'm going to do is I'm going to subtract 6 on both sides. So the left side is going to be x minus 6. The right side is going to be 3y. The next thing that I need to do is I need to divide everything in here by 3. Now, that x, you didn't see it, but there is a number in there. It is the number 1. That is 1x. So when I divide these, that is going to be 1x divided by 3, or what I will call 1 over 3x, means the same thing, minus 6 divided by 3 is 2, and that's equal to 3 divided by 3, which is 1y. And I hope that you notice that 1/3 x minus 2 is exactly what we found when we found the inverse. So what you need to know about inverses is this. If you are given points, then the inverse is found by just flipping the x and the y. If you are given a graph, the inverse is it flips over the line y equals x. And if you are given an equation, you're going to change the y and the x, and then you're going to solve it for y. That's just something that you need to know about when we start talking about inverses. So let's continue on here. So when finding an inverse, then what we're going to do is if we are given a function, all of your x and y coordinates switch. We switch them. If you're given a set of ordered pairs, you can just reverse the order. You can go from xy to yx. If you're given an equation, you change your y's to x's, x's to y's, and then solve that thing for y. That will give you the new function. The new notation that you need to know is if you have f of x, its inverse is going to be f with a -1 of x. If you have g of x, then the inverse of g of x would be g -1 of x. If you had h of x, the inverse of h would be h -1 of x. So just like you can name new functions using different letters, you can also do their inverses the same way. Now, one of the things that you need to know, if you think about domain and range, the domain is the list of all the x's, and the range is the list of all the y's. So if the inverse changes x's to y's, then the domain and the range will switch as well. The domain of a function will become the range of its inverse, and vice versa. The range of a function will become the domain of its inverse. And if you're thinking back to your geometry days, if you think about the graph, all you have to do is reflect the graph over the line y equals x. If you do a geometric reflection over the line y equals x, then you're going to get the inverse as well. So inverse are things that you've already done. You just didn't know that you were doing them. So let's take a look at this example. So here we go. So it says graph the line f of x equals 2/3x minus 2. So if I want to graph this, I need some points. So I'm going to do the -2, the y-intercept, and then the slope is 2/3. So I'm going to rise 2, 1, 2, run 3. I can rise 2, run 3, rise 2, run 3. And if I want to keep going, I can go down 2, left 3, down 2, left 3, down 2, left 3. Those are all common points that are going to show up on there. So we graph that. We're going to call that f of x. And then it says darken in a few. It wants 3. I'm going to just pick 3 points. I'm going to do the point 0, -2. And then we did 3, 0. And then that far right one is 9, 4. Those are the points. If I want to do the inverse, I just reverse those points. Instead of 0, -2, I'm going to do -2, 0. Instead of 3, 0, I'm going to do 0, 3. Instead of 9, 4, I'm going to do 4, 9. So I'm going to just graph those points. So the point -2, 0 is right here. 0, 3 is up here. 4, 9 is way up here. And then I'm going to go ahead and graph that point. And it wanted me to call this, that was blue was f of x, so this is going to be f inverse of x. So what would be this new equation? So if I just look, it's going to be y equals the slope. I'm going to count right here. I'm going to rise 1, 2, 3, and run 1, 2. So it's 3 over 2 is my slope, x. And the y-intercept, it crosses at positive 3. So y equals 3 over 2x plus 3. Now, what do we notice about the two equations? I hope you notice that that is a reflection over the line y equals x. Let's graph that line. Here it is. I'm going to put in y equals x. There's the line y equals x. You're going to see the line y equals x. Again, if I wanted to go through and, like I did in that first one, if I wanted to go in and connect these, if I wanted to connect those, the midpoints of those yellow segments are on the line y equals x. There is the point -6, -6. If you look down here, right here is the point -6, -6, where x and y are the same. And it is on the red graph, it's on the blue graph, and it's on the yellow graph. That point shows up on all of them. That will always happen. So what do you notice here? That's a reflection. We just said that. Right? It is a reflection over the line y equals x. Sorry. All right. The next example is one of our other parent functions. This is y equals x squared, or f of x equals x squared. You'll see it's already graphed for us. And it wants to know, is this original graph a function? Remember, in order to know whether it is a function, you need to use the vertical line test. Does this thing pass the vertical line test? Is there a vertical line that ever touches more than once? There is not. This does pass the vertical line test. That means it is a function. Is this original graph one-to-one? Remember, we talked about, does it pass the horizontal line test then? If it is a function, does it then pass the horizontal line test? And this one fails the horizontal line test. If I draw a horizontal line in here, you can see that that hits in two spots. So is it one-to-one? No, it is not. Is this even, odd, or neither? This is even because it is symmetric over the y-axis. Part B then wants us to flip our ordered pairs. So I'm going to look here first. My first ordered pair is -2, 4, so I'm going to flip that to 4, -2. The next one here was -1, 1. I'm going to flip that to 1, -1. The third one, 0, 0, flips and stays 0, 0. The fourth one, 1, 1, switches to 1, 1. And then 2, 4 switches to 4, 2. It says graph this. So I'm going to plot these points. So 4, -2. So right 4, 1, 2, 3, 4, down 2. 1, -1. 0, 0, 1, 1, and 2, 4. Now, hopefully you realize this is a sideways looking parabola. So this is not a straight line here, but it is a curve in there. And then it's going to continue out. And it's going to continue out. So it's going to look something like that. Graph the line y equals x. Like we've done all these times. But there's y equals x. You will notice it touches two of the points. It touches 1, 1 and 0, 0. Because that's when x and y are the same. And then it's going to ask me some questions about our red graph. Is the red graph a function? Does it pass the vertical line test? And the answer is no. And here's what you should understand. The vertical line test of the inverse is like the horizontal line test of the original, and vice versa. So it's always just switching x and y. So kind of keep that in mind, that as I'm thinking about inverses, I'm just always thinking switch x and y. Everything about x switches to y's. Is the new graph 1 to 1? Yes. The red graph passes the horizontal line test. And is the new graph even? No, because it's not reflecting over the y-axis. Is it odd? No, because it is not symmetric around the origin, so it is neither. Be careful, some people like to say, well, no, that looks like it is rotationally symmetric. If you were to rotate this graph completely upside down, that red sideways looking parabola would be facing the wrong direction. It would be facing to the left and not to the right. So it is not symmetric. So what does that mean as a rule? That means a function must be 1 to 1. It must pass the horizontal line test. If it passes the horizontal line test, then its inverse will pass the vertical line test. So when you take a look at a picture or a graph, you can quickly see if it fails the horizontal line test, then its inverse will not be a function. And that's going to be a big part of Algebra 2. One of the things that we're going to ask is we're going to give you problems that look like this. And it's just going to say, determine whether its inverse is a function or not. So all I have to do is actually run the horizontal line test, and it will tell me the results of the inverse's vertical line test. So in part A, that horizontal line touches twice, so is the inverse a function? No, failed the horizontal line test. For B, does it pass the horizontal line test? No, its inverse is not going to be a function. For C, does it pass the horizontal line test? Yes. That means C's inverse will be a function. X cubed. So here's what I'm going to do. Since I could put these in Desmos, but I remember this is the one that looks like it changes lanes. Y equals 2x squared minus 1. This is in the family of this parent, x squared. Y equals negative 6 is in the parent of a horizontal line. Y equals negative 3x plus 7 is in the parent of lines. Y equals the square root of x has this parent. I'm just going to think about the parent functions, that's all. Y equals x squared. It passes the horizontal line test, even right there in the middle. It does pass, so yes. Y equals 2x squared minus 1. If it is an x squared, it's going to look like a parabola. Parabolas do not pass the horizontal line test, so it's going to be a no. Y equals negative 6 is a horizontal line, so it fails the horizontal line test. The answer is going to be no. A linear equation, if it is a linear equation, linear equations pass the horizontal line test, so yes, its inverse will be a function. The square root function we saw yesterday, it does pass the horizontal line test. So yes, its inverse will be a function. And again, if you don't like just sketching the graph out by hand, right, the other thing you could have done is I could have just done y equals x cubed, and then I could have just kind of taken a look at the picture, and I could have seen, yes, that's going to pass the horizontal line test, right? Looks something like that. And then if I wanted to do the next one, y equals 2x squared minus 1, you would see that that fails the horizontal line test, right? We had one of the other ones, I'll do g as well, so you can see it, y equals negative 3x plus 7. I could have just graphed these in and looked at the graph of them to see if they would pass the horizontal line test. But one of the things that you really just need to understand, if your question is this thing's inverse a function, just check and see if it passes the horizontal line test. If it does, it's a function. If it doesn't, it's not. All right, hope that helps.